So Chapter 7 is a lovely little 4-page chapter, which is Introduction to Thermal Agents. There are actually more pages in the PowerPoint than there are in the chapter. There are more words in the chapter. But basically we're going to define some terms having to do with thermal agents and just what different agents fall into different categories. So we're going to talk about specific heat and modes of heat transfer. The learning objectives that I want you to get out of this, I want you to be able to define specific heat and its application to the use of thermal agents. I want you to define and provide examples of conduction, convection, conversion, radiation, and evaporation as modes of heat transfer. I want you to be able to identify and describe the components of the rate of heat conduction. I want you to define thermal conductivity and provide examples of high, moderate, and low thermal conductors. And I want you to state the significance of specific heat and thermal conductivity in a therapeutic environment. So pretty straightforward, I think. So the principal modes of heat transfer are conduction, convection, conversion, radiation, and evaporation. And we're going to talk about specific heat and thermal conductivity with its relationship to conduction. So conduction is an energy exchange by direct collision between molecules of two different materials at different temperatures. In other words, things are touching. So that's the direct collision of molecules part. So conduction requires direct contact of the targeted area with the heating or cooling agent. So basically the faster moving molecules in the warmer material collide with the molecules in the cooler material, causing them to accelerate, and it increases the heat of the cooler side. So you can sort of think of it as heat transfer. You're moving heat from one thing to another. So whichever side's cooler is going to pick up heat from the hotter side, if that makes sense. So examples of conduction are a hot pack or a warm paraffin. The heat goes from the agent to the patient. Or an ice pack, the heat goes from the patient to the agent. So the heat is moving from whatever is hotter to whatever is cooler. So if your agent is hotter, it's moving to the patient. If your patient is hotter, it's moving to the agent. So you're melting an ice pack with heat from the patient, if that makes sense. Specific heat is the amount of energy required to raise the temperature of a given weight of material by a given number of degrees. So it's usually the numbers that you get from it. It's usually a cubic centimeter of material by 1 degree Celsius. So different tissues or materials have different specific heats. So skin has a higher specific heat than fat or bone. Fat or bone has a higher specific heat than water. Water has a higher specific heat than air. So if you think of it, it's going to take more energy to heat up skin than it is to heat up fat or bone. It's going to take more energy to heat up water than it is to heat up skin, to heat up skin than it is water, and more energy to heat up water than it does to heat up air. So materials with a higher specific heat require more energy to heat up. That's what I'm trying to say here. I said it in an awkward way though. And they also hold more energy at a given temperature. So if you had, let's just say you had a tank filled with air that was at 90 degrees, and you walked into it, it's not going to hold that temperature for very long. If you had a tank full of water at 90 degrees, it's going to hold its temperature longer. It's going to hold energy longer. So that's one of the reasons why we store water in a hot water heater in our house, so we can have hot water to bathe with or wash our dishes with, because water is a good way to store energy. But I don't have a tankless hot water heater, it's different. Anyway, so this is the specific heat of various materials. And this one is the heat is in joules per gram per degree of Celsius. So how many joules does it take to heat up a gram of that material 1 degree Celsius? So water has a very high specific heat. Bone has a very low specific heat. Air has a very low specific heat. So air is not going to hold temperature. Water is going to hold it better. Skin is going to hold it better than bone. Okay, you just comparison. So thermal conductivity, and then we'll talk about how that affects modalities. Thermal conductivity is the rate at which material transfers heat by conduction. So how fast does the heat transfer? So we talked about the molecules crashing into the other molecules. How fast does that happen? How fast does the heat from the hot side go to the cold side? So thermal conductivity of various materials. Obviously, metals have a higher thermal conductivity than other materials, and different kinds of metals, different. So air doesn't have, there are not very many molecules close together in the air, so they're not going to transfer heat very fast. So you're going to get more heat from hot water than you are going to get from hot air. The thermal conductivity is greater. And you're going to get more heat from metal than you are going to get from water or air. Hopefully that makes sense. So when we talk about the safety of hot packs and cold packs and things like that, that's where that comes into it. So the higher the thermal conductivity of something, the less safe it is going to be to heat somebody's tissues using that. The more chances for burn. So if you have something with a very low thermal conductivity, it's probably not going to be very effective at heating. If you have something with a very high thermal conductivity, it's probably not going to be very safe. So you want something in between. So safe and effective rate of heat transfer to patients requires that materials with high specific heat and moderate thermal conductivity. So like ice and a pillowcase cover on the ice pack, that's the moderate thermal conductivity. So we want it to make sure that the initial difference in temperature is well tolerated, meaning that when you stick the hot pack or cold pack or water or whatever on the patient, it doesn't hurt them. So insulators like towels hold air and they limit the rate of heat transfer. So that's why if you're doing a hot pack, you want to use a lot of layers of towels, because the fluffiness of the towel holds air, and air has low thermal conductivity, and so it limits the rate of heat transfer. So I don't think I'm going to test you on the formula for the rate of heat transfer, but I want you to know the components of it and how it affects treatments. So the area of contact times the thermal conductivity times the temperature difference divided by the tissue thickness. So it makes sense. If you had something with covering a wide area with moderate thermal conductivity and a moderate temperature difference, and really thick tissue, you're going to get a slower rate of heat transfer than if you had thin tissue in a smaller area of contact, or smaller thermal conductivity, or less of a temperature difference. So if you're trying to, like I'm going to make myself a cup of iced coffee, or a glass of iced coffee, because I like iced coffee. I like hot coffee too, but anyway. If I do it by brewing hot coffee and putting ice in it, there's a greater temperature difference. So I'm going to get, the ice is going to melt faster because I have a greater rate of heat transfer. If I did a cold brew in the refrigerator, which is what I usually do, and put ice in it, the ice is going to it's going to melt slower because I have a slower rate of heat transfer. The temperature difference is not as great. Hopefully that makes sense. Maybe I need to make myself a cup of coffee. Okay, convection is heat transfer by direct contact between a circulating medium with another material of a different temperature. and it transfers more heat than conduction because the molecules in the circulating medium are contacting more molecules. The energy is being circulated. So the examples of convection are a whirlpool, or just a pool. It doesn't necessarily have to be a whirlpool, and fluidotherapy. And we have some pictures of fluidotherapy in the heat thermotherapy lecture. Circulating blood also helps maintain physiological temperatures by convection. So it takes the warm blood from the core of the body, takes it out to the cold areas in the extremities, and circulates it to maintain your body temperature. So convection transfers more heat than conduction because more molecules are coming into contact with the cooler tissues. Conversion converts a non-thermal form of energy into heat. So it converts mechanical, electrical, or chemical energy into heat. So ultrasound is an example of mechanical energy. It converts mechanical vibration of the molecules into heat in the tissues, if you're doing it in a thermal application, and we'll talk more about that. Diathermy uses electromagnetic energy to heat up body tissues, basically. Mechanical, it's like rubbing your hands together when your hands are cold, to use mechanical energy to convert energy into heat. Okay, or soft tissue mobilization. Same thing, you can heat up the tissues that way. But unlike heating by conduction or convection, the temperature of the thermal agent isn't important. It doesn't require direct contact. There might be other electrical or mechanical effects besides heat on the body. Like with ultrasound, there's definitely other mechanical effects. But you're not actually touching the diathermy or the ultrasound to the tissues that you're heating up. Interesting. Radiation is a direct transfer of energy without the need for an intervening medium or contact. So a heat lamp, an infrared heat lamp, transfers by irradiation. The rate of the temperature change depends on the intensity of the radiation, the relative sizes of the source and the treatment area, and the angle and distance of the radiation to the treatment area. So we are not going to do infrared lamps in lab, and you're probably never going to see one in the clinic. But the idea of radiation, also like the sun heats you by radiation. There's no intervening medium or contact. Evaporation, energy is absorbed to change a liquid into a gas or a vapor. So the material that contributes the energy for the evaporating liquid is cooled in the process. So a vapocoolant spray or sweat evaporating off your skin, it cools the skin and it turns into vapor. So ambient humidity in the air impairs evaporation, so it slows down heat transfer. Makes sense, right? So it's sort of the like the pool that we have in my clinic. It's about 95 degrees. It's a warm therapeutic pool. So when it feels hot, or to me, it feels warm in the pool room, in the enclosure, and you get in the water and the water's warm, and then when you get out of the water's evaporating off you and it feels cold in there. So that's our transfer of heat by evaporation.